Hi everyone. Here we have a series of questions to help us understand universal gravitation a little bit better. First one says, suppose Earth had no atmosphere and a ball was fired from the top of Mount Everest in a direction tangent to the ground. So, tangent over here. If the initial speed were high enough to cause the ball to travel in a circular trajectory around Earth, the ball's acceleration would, and then you have these answer choices. Before you pause the video and think about it, I want you to consider, where is it that we get G from? Hopefully you remember from the lesson. And go back to your notes, follow the mathematical procedure to find G, and then see if throwing the ball from this height would affect this number, or how much it would affect it. Pause the video, and I'll see you in a bit. All right, so to find G, we have to think of the weight of the ball. That's just its mass times the acceleration of gravity. And that's going to be equal to Newton's law of universal gravitation, where capital M is the mass of the Earth, and this M is, of course, the mass of the tennis ball. You can see that this will cancel, and we have G in this form, where this is the universal constant. All right, so what's going to change if we throw from Mount Everest? Well, the radius, or the distance to the center of the Earth, is going to change. Let's see. The radius of the Earth, let's call it R. It's going to be 6.38 times 10 to the 6 meters. And the height of Mount Everest, let's call it H, is about 8,850 meters. So to find the new G, if you will, call it G prime, we would need to multiply the universal constant times the mass of the Earth, and then divide by R plus H, and then square that. Let's see what this would be, R plus H. So there we have it, 4.08 times 10 to the 13th. Now, if you compare that number to the original radius of the Earth, there's not that big of a difference. So if we were to plug in this quantity, the 4.08 times 10 to the 13th, into this equation, you'd get a number close to G. Now let's see how close it would be. And there we have it, 9.77 meters per second squared. So G prime would be 9.77 meters per second squared. And I think you can see rather easily that this is approximately G. Moving on to question 2, we have two satellites, A and B, of the same mass, are orbiting Earth. The distance of satellite B from Earth's center is twice that of satellite A. What is the ratio of the speed of A to that of B? So what I want you to think about before I pause the video is, what does this mean? How can you write this mathematically? And then I want you to think about, all right, these two satellites are undergoing circular motion. What's required? What's needed? Think of the level we talked about. And then I want you to think, what force is getting that level? Then think about, okay, if I want to know the speed, what equations can I combine to find a relationship between what's causing this motion in a circle and the speed? Pause the video. I'll see you in a bit. Right, the first thing I want to know or want to write is that I know distance B equals twice distance A. That's going to be important for me to find that ratio. Now, for satellite A and B for that matter, they can undergo circular motion because you have a centripetal force. Now, that centripetal force for either satellite happens to be the gravitational force, and we know that the equation for this is universal constant, the product of the masses, times the distance squared. This distance is going to be the distance to the Earth. All right. And that's the same for both, okay? That's the same for both. So then we know that this is a centripetal force, and we know the centripetal force as it pertains to speed or velocity is mv squared over r. Then you can see how if we take into account only these two terms, we can cancel out the mass of the satellite, and we have, I'm going to use the reflexive property, v squared over r equals, I'm going to write constant, universal constant here as a strategy. You'll see why. Then this r is going to cancel the square, and I end up with v squared equals capital G times the mass of the Earth divided by the distance. So I can use this equation now for satellites A and B. We had picked, we haven't picked any colors. So for satellite A, I'm going to pick purple, and for B, I'm going to pick green, because why not? So for A, velocity A squared is universal constant, mass of the Earth, divided by distance A. For B, it is similar, with the only difference that I'm going to have distance B. However, I know that distance B is twice distance A. So I can say that velocity B squared equals universal constant times mass of the Earth times twice radius A. So now I can find the ratio, I'll take the square root later, between these two, because I'm going to divide the left sides and I'm going to divide the right sides. Let me move this over here so I have more space. Okay. So we have okay, so here we have it. And if you're good with algebra, you can solve this one very, very easily. If you are a little rusty with your algebra, all we got to do is, instead of dividing two fractions, because these two are fractions, I'm going to get the reciprocal of this one and multiply instead. There we have it. Now we can cancel G, M, distance A. And we remain with a 2. And you got to be careful, the answer is not C, because we still have to take the square root of the left side. So the ratio of the speeds, velocity A over velocity B, equals the square root of 2. The answer is D. Number 3. The space shuttle orbits about 200 kilometers above the Earth's surface. The shuttle's pre-launch weight is its weight measured on the ground, neglecting fuel. The magnitude of the force of gravity on the shuttle while it is in orbit is. What I want you to think about this one is, what do they want you to find? What is the magnitude of the force of gravity? Think of what that means here on Earth. What is the magnitude of the force of gravity on you? What do we call that? Pause the video. All right, hopefully you know that means weight. They want to know what is the weight of the space shuttle when it is in orbit. And This one is very similar to number 1 because we have 200 kilometers. It is 200,000 meters. So the weight is going to be less because it is farther away from the center of the Earth. But it's not that far. So let's do the math real quick. From our notes, we know that G is this, where R is the distance to the center of the Earth. So let's call this new G, G prime, when you are in orbit, or the space station, space shuttle, whatever. You have the mass of the Earth divided by radius of the Earth plus, let's call this new distance, 200 kilometers, D, then squared. So the new weight, let's call it W prime, it's going to be the mass of the space shuttle times G prime. So because we don't know the mass of the space shuttle, we just have to find, okay, what's this new G prime? If it's close to 9.8, then the weight would be about the same. So I'm going to use the same stuff I used before. Instead of adding the Mount Everest, I'm going to add the 200 kilometers. So that's 200 kilo, that's 1,000. There you go. So the new G is about 9.2, which is close to 9.8. That means the weight of the shuttle is going to be slightly less, right? Because G is less, so it's going to feel a little bit less attracted to the Earth, so it's going to feel a little lighter, so slightly less, because G prime was less than G, slightly less. Let's move on to the next question. At some instant in time, two asteroids in deep space are a distance r equals 20 kilometers apart. Asteroid 2 has 10 times the mass of asteroid 1. What is the ratio of the resulting acceleration due to gravitational attraction to each other? All right. So for this, I want you to think of Newton's second law of motion and how you can combine Newton's second law of motion with the universal law of gravitation. Pause the video. All right. So Newton's second law of motion is force equals mass times acceleration. So because this is a force, then we can use the same formula for universal gravitation. All right, let's see what we know. So for acceleration 1, we're going to have mass 1 times acceleration 1 times G m1 times m2 divided by r squared. R is the same because they're 20 kilometers apart. So we can cancel mass 1, and we have acceleration 1 equals capital G m2 over r squared. For A2 is going to be the same thing, with the exception of the masses. There we have it. If we divide these two sides, then we can cancel G and r squared. So then we have A1 over A2 equals M2 over M1. And if we plug in what we know, we have 10 meters over 1 meter. So then I think you can see that the answer would be 10 to 1. For the last question, the moon does not fall to the earth because, I'm not going to give you the answer to this one. Think about it. We'll talk about the answer when I see you guys again. Bye.